Okay, thank you. Good morning, everybody. My name is Pablo Valdivia. I'm a research scientist with the Mechanical Engineering Department at MIT and also with the Singapore MIT Alliance. Today I'll be talking about a bio-inspired whisker sensor for underwater applications, probably among the few mesoscale sensors in this conference. So let me start first by our motivation. And our motivation is shown here in a couple of pictures. And it is pinniped whiskers. Pinnipeds, seals, sealions, etc. use their whiskers only to track prey underwater. They don't use vision, they don't use sound, they only use the underwater tactile sense that they get from their whiskers. And they're able to do this because of a couple of reasons. The first one being that their prey, which is mostly fish, they leave a very distinctive wake underwater when they move. And this wake has been studied very well in the literature. It's called an inverted von-karman wake. And this wake leaves very strong fluid disturbances that can last for seconds or even minutes after a fish has swum by a particular point in space. The second reason is that, or that's being hypothesized at the moment, is the particular geometry of the whiskers. And I'm showing here a picture of two of the whiskers from a seal with an inset that zooms in a little bit further. And when you look at the pictures, you can see that there's undulations along the length of the whiskers. The whiskers have an elliptical cross-section, and the undulation actually is off-phase from one side of the axis to the other. And the hypothesis is that this particular geometry minimizes or eliminates completely vortex-induced vibrations, which would be the main source of noise when you are trying to measure something underwater by towing a cylinder, right? And if you're not familiar with vortex-induced vibrations, essentially when you have a cylinder that you're towing in cross-flow, the vortices are going to start being shed at some range of number, and the loading from these vortices is going to force the cylinder to oscillate, sometimes uncontrollably. And of course, this is a large source of noise if you're trying to sense flow disturbations. And this type of sensing is very robust. It's been studied already for a couple of years. Seals are able to track very well prey. This is a picture from a paper by Schulte where you see two tracks, one blue and one red. The first one is a track left by a prey, quote unquote, in the experiment. And the second track is shown in red is the track that the seal follows, tracking that prey after a couple of minutes. And you can see they match very well. So this type of sensing is very robust. Now, most of the work so far has focused on the geometry of the whisker as the main basis for sensing. Our work focused a little bit more on the mechanical transduction of the signals that come from the whisker. So each whisker is supported by a follicle that is in the face of a seal or a sea lion, and you can see this follicle zoomed in here. It's itself surrounded by muscles. And if you zoom even further, you can see there's a very complex structure, full of nerve endings and very complex. I won't go into much details, but the salient features are that mechanically the whisker is supported mostly at the upper neck of the follicle, and it's clamped at its base where the major nerve ending leaves. This is the deep vibrisal nerve. So with that understanding, we start by developing a very simple model of the follicle axis of this. Our assumptions are stated here, and they're essentially that there's not going to be any high order vibrations excited on the whisker as we are doing sensing underwater, meaning that the oscillations of the whisker are only going to be in the plane, and secondly, the modulus of the whisker shaft is much higher than the modulus of the follicle, which is the case. The whiskers are made of keratin, which has a modulus in the order of gigapascals, and the soft tissue in the follicles have modulus in the order of a couple of hundred pascals or kilopascals. And finally, our main assumption is the viscoelasticity of this follicle has a strong influence on the measurement. So we're modeling the planar dynamics of the whisker vibrating in the flow, essentially using the combination of torsional and linear spring dampers to model the dynamics of the follicle. And this is essentially going to be a forced oscillator, right? And of course, this is a second order system. It's very well understood. The frequency response is very well understood. This is the transfer function. Now, if you have this as a sensor, it's very interesting, right? If you can make such that the noise that is commonly present in your experiments or in your applications falls in the roll-off area, is by default damped or not amplified, right? And if your frequencies of interest fall very close or at resonance, you have a very high signal-to-noise ratio. So we're going to attempt to do this with our sensor. The conceptual design is very simple. I'm showing here a diagram with a cutout, so you can see better the inner workings. The sensor capsule is essentially mimicking the follicle sinus complex. We have a viscoelastic membrane here that supports the whisker shaft, and it allows it to pivot. At the base of the whisker, we have 4 flexible sensors, which are essentially flexible potentiometers that are going to be measuring the deflections of the whisker, the oscillations of the whiskers in 2 perpendicular planes. One in line with the motion of the whisker, and the other one perpendicular to it. Now, the material properties, of course, are given by the viscoelastic property of the membrane and the material properties of the flexible sensors themselves. And this is an explorative view of how we mount one of these sensors in a little hole to test its dynamics. This is a slightly larger cross-sectional view. It's a very simple sensor. And of course, we are starting with one sensor, and eventually we are going to study arrays as well. This is the actual prototype. The scale of the sensors is around 25 centimeters, which is a little bit over twice the size of the whisker of a real seal. You can see here the flexible displacement sensors, the viscoelastic membrane, and we are testing 4 types of whisker, artificial whiskers, I should say. One is our control experiment, which is basically just a cylinder. On the other end of the spectrum, you have a artificial whisker that tries to mimic the exact geometry of the real whisker with the undulations along its length, and also a major curvature along the length of the whisker. And in between, we have special cases. We have a whisker that has the undulations but is straight, and we have a whisker that is basically a whisker that has an elliptical cross-section as opposed to a cylinder. In terms of design guidelines, since this basically behaves as a second-order system, it's very easy to design the frequency that can be amplified, right? We can estimate the natural frequency using this equation. Now, in the case of our sensor design, the material properties of the linear stiffness and damping are pretty much set, because we're using commercial flexible sensors, right? But we still have 2 design parameters, which are the material properties, the stiffness and the damping of the viscoelastic membrane, which we can control by the material and the geometry of the membrane, to design basically what frequency we want to amplify. And these are some experimental results. We're basically towing the sensor in a water environment that was previously quiescent. To give you an idea of the color coding here, we have the whisker that is being towed at a towing frequency UW. The signals from the sensors perpendicular to the direction of motion are shown in blue and in red, and the signals from the sensors in line with the direction of towing are shown in green and in yellow. And I'm showing here 2 towing speeds, 0.1 meters per second and 0.3 meters per second. You can see the step as soon as we start the towing at the two different velocities. So the steady state signal, the mean value is proportional to the towing speed. So this can be used as a velocity sensor as well. And the frequency content and the amplitudes of the oscillation are going to be proportional to the disturbances on the sensor, if there's a wake or any other interesting hydrodynamics around it. Finally, if we look at the power spectral density, we can see that the whisker geometries do minimize VAV. I'm showing here the two graphs on the top are power spectra from an experiment using a cylinder. So this doesn't have the geometry that's supposed to eliminate VAV, right? And the two graphs at the bottom are actually using a whisker model. So this has the geometries of a real whisker. So, and you can see the vertical black lines mark the frequencies at which theoretically VAV should appear. So when you look at a cylinder, you can see from the spectra that there's actually VAV going on here. And by the way, I should say that for all these experiments, the viscoelastic membrane was, the material properties were chosen such that the resonant frequency was well before the theoretical vortex-induced vibration frequency. So in principle, that also should minimize any appearance of VAV. But at slow speeds with a cylinder, we still see it, which suggests that it's a very strong phenomenon that you need more than the natural frequency of the system alone to kind of minimize it. At high frequencies, you don't see it anymore, and I guess we can attribute that to the way our sensor was designed. And when we use a whisker, we don't see it at all. So the combination of the geometry of the whisker and the way we place the natural frequency of the sensor completely eliminates the appearance of noise. The next step was to see how well we can make out interesting fluid dynamics, and we did this by scanning a von-karman wake left by a cylinder. We tow a cylinder and we generate what is known as a von-karman wake, and I'm showing particle image velocimetry image here. I'm showing the vorticity contours. So this is the wake of the cylinder, and this is the whisker, the position of the whisker as it's being towed inside the wake. Right, and I'm showing here two snapshots in time. The yellow point shows the location of the whisker, and this is the reading of one of the sensors perpendicular to the direction of motion. And each time the whisker intersects a zone with strong vorticity, we see a peak in amplitude. So this is the status of the sensor at the moment. We have confirmed that the follicle sinus complex dynamics play an important role in sensor sensing. On the bench, we put a very simple model to explain this dynamics, which is essentially a second-order system. Because of this, we can very well choose the frequencies that we want to amplify. We also verify that the whisker-like geometries minimize vortex-induced vibrations. And a sensor that has these type of properties, in particular, being able to tailor the frequencies that you can amplify, is has very high importance in underwater applications, mostly for underwater robotics. Okay, so I think I'm close to running out of time, so let me finish here, and I'll be happy to take your questions. Thanks.